In this video, we're going to take a look at solving linear equations in one variable. If I have an equation in one variable, in other words, a one variable equation, then a solution to that equation is a value for the variable that makes the equation true. So for instance, if I have 3x minus 4 is equal to -1, a solution to that equation is x equaling 1, because when I plug in the value of 1 in for x, I get 3 times 1 minus 4 is equal to -4, which simplifies to -1 is equal to -1. Therefore, since I got a true statement, that means x equals 1 is a solution to that equation, that one variable equation. Now, a linear equation is an equation in one variable. A one variable linear equation is an equation that has variable x being raised to the first power. So we have x not being squared or not being raised to the third power or anything like that. It's always just x raised to the first power when I multiply things out and simplify. Another way to describe a linear equation in one variable is that it's an equation that can be written as a times x plus b is equal to 0, where a and b are real numbers and a is not equal to 0. So we have our variable x raised to the first power. Now you can use any other variable that you want, but a lot of equations will have the variable as x. So we're going to solve linear equations in one variable. If we want to solve linear equations, the big idea is that we create equivalent equations by doing the following things. We can simplify both sides of an equation. That's not going to change the answers to equations, so that'll just create an equivalent equation. By equivalent equation, I mean one that has the same solution. So simplifying both sides of an equation does not change the solution. It just creates an equivalent equation. Another thing that doesn't change the solution is to force our variable terms on one side of the equation. Then we'll force our constant terms on the other side of the equation. And we'll do so by adding or subtracting terms from both sides. After we've done that, then we'll divide by the coefficient of the variable. So the steps to solving a linear equation: first, we simplify both sides. Second, we're going to force the variable terms on one side. Third, we're going to force the constant terms on the other side. And then last, we divide by the coefficient of the variable. Let's take a look at this equation. We have 3x minus 4 is equal to 17. I'll go ahead and solve this one. So the first thing that I would do is I would simplify both sides of the equation. That's actually already done for me because 3x minus 4 is as simple as I can make the left-hand side. 17 is as simple as I can make the right-hand side. 3x minus 4 cannot be combined because those are not like terms. And so the next thing I would do is I would add 4 to both sides. The reason I'm adding 4 to both sides is because this 3x is the only term with the variable x in it. So that's on the left-hand side. So I want to force all of my constants onto the right-hand side. I do that by adding 4 to both sides. Usually, for the purposes of this video, I typically don't write out +4 underneath, but a lot of times if I'm doing this on the board, I'll write +4 underneath. Or you could think of adding 4 to the left, adding 4 to the right. Okay, you could put it underneath. That's what I usually do, or off to the right or something like that. But when I add 4, the -4 and the +4 cancel out. They give me 0. I'm just left with 3x on the left-hand side. And on the right-hand side, 17 plus 4 gives me 21. Then lastly, I'll divide both sides by 3. And again, usually I write that on the board as just division as the fraction symbol over 3. Because 3 over 3 is 1, and 1 times x is x, I just get x on the left-hand side, and 21 over 3 simplifies to 7. So this is the solution to this equation. 3x minus 4 is equal to 17. By the way, that is going to be the only solution that exists, because in general, most of the time in linear equations, we get one solution. We can get all real numbers or no solutions either, but most of the time in this class, we'll get one unique solution, like x equals 7. You can always check your answer as well by plugging in the solution and seeing that the left-hand side and the right-hand side of the equation simplify to give you a true statement. 3 times 7 minus 4 is 17. And on the right-hand side, we have 17. So that's true. Therefore, I know for sure that 7 is a solution to this linear equation. Equations can get more complex, and there might be more simplification needed to solve a linear equation, like here in example 2. But the same principles will hold true. We want to get both sides as simple as possible, then get our variable terms on one side, then get our constant terms on the other, and then divide by a coefficient if need. Again, in each step, that's always if needed, if it's already not done for us. So let me show you how to do this equation. The equation is 5 times the quantity x minus 2 plus 10 is equal to 3x plus 18. I need to start simplifying before I can do any moving of terms to one side or the other. So what I would do is I distribute this 5. 5 times x is 5x. 5 times negative 2 is a minus 10. Then I have plus 10 is equal to 3x plus 18. Now the right-hand side I didn't do anything to because it's already as simple as I can make it. These are two terms that are not alike. On the left-hand side, I can do one more simplification step. We have 5x minus 10 and plus 10. The minus 10 and the plus 10 are going to add together to give us a 0. So I get 5x is equal to 3x plus 18. Now at this stage, I would subtract 3x from both sides. That would give me all of the terms with x's on the left-hand side And in order to keep equivalent equations, we always have to do the same thing to both sides. So in order to keep equivalence, we'd have to subtract 3x on the left and subtract 3x on the right. When I subtract 3x on the left, I end up with 2x. When I subtract 3x on the right, I end up with 18. Now, in this case, there's no constant term that I need to also move around. In the last case, I had to add the 4 to both sides. Here, at this stage, I already have 2x isolated equaling 18. That's isolated. So all I have to do is to divide both sides by 2. If I divide the left-hand side by 2, 2 divided by 2 gives me 1. 1x is just x. On the right-hand side, 18 divided by 2 is 9. If you wanted to confirm that that is the actual solution, you just plug it in. We take 5 times the quantity 9 minus 2 and then add 10. Set that equal to 3 times 9 plus 18. If I take, that's going to be 5 times 7 plus 10. 5 times 7 plus 10 is 45. 3 times 9 is 27. 27 plus 18 is also 45. So plugging in 9 does, in fact, give me a true statement. So x equals 9 is the solution to this linear equation in one variable. Let's go ahead and do a couple of other examples. I want you to solve these two equations. Now, here we have different variables. We have variable y in the first equation on the slide and variable z in the second equation. That's not going to make any difference as far as the technique of solving. So why don't you push pause on the video, try to solve these two equations. In a couple of seconds, I will come back and show you how these are done. All right, in this first equation, the one that involves y, the left-hand side is as simple as I can make it. The right-hand side is as simple as I can make it. So what I would do is I will get the y terms on the left-hand side of the equation by subtracting 4y from both sides. Subtracting a number from both sides gives me an equivalent equation. So take 9y minus 4y minus 7 and set that equal to 4y minus 4y plus 15. I will get 5y minus 7 is equal to 15. Then I would add 7 to both sides. 5y minus 7 and then plus 7 on the left-hand side. On the right-hand side, 15 plus 7 will give me 5y is equal to 22. Then divide both sides by 5. If I divide the left-hand side by 5, I get 5y over 5. On the right-hand side, I get 22 over 5. So that gives me y equals, and this kind of depends on how it asks for the answer. If it asks for the answer as a mixed number, it'd be 4 and 2/5. If it asks for an improper fraction, it would be 22 over 5. If it asks for a decimal, the decimal version would be 4.4. You can plug that back in, that 4.4 back into the equation and see that you do indeed get a true statement. I won't show that step, but we just continually created equivalent equations. And what you're allowed to do is you're allowed to add or subtract the same number from both sides. You're allowed to rewrite how a side looks, like do the algebra, and you're allowed to divide or multiply both sides by the same non-zero number. All of those things maintain equivalencies. Let's go ahead and do that for the equation involving variable z. The first thing I would do is simplify. 2 times 3z is 6z. 2 times -1 is -2. Then I have minus 5z is equal to 32. Combining like terms, 6z minus 5z is 1z, or just z. Now all of the variable terms are on the left. So what I would do is I would add 2 to both sides. And I would get a z value that's equal to 34. In the future, I might not write every single step. I might just audibly say that step. But here z is equal to 34. Once again, you can check that out by plugging it in to that original equation and seeing that you get a true statement. In this case, you do. Let's try a couple more equations. Let's solve these two. One involves the variable x and the other involves the variable y. Go ahead and push pause on the video, try these, and see what happens. I will show you how to do these in just a couple of seconds. In this first equation, on the right-hand side, there's a lot of simplification that can be done. On the left-hand side, it's as simple as we can make it. So on the left-hand side, it's still 5x plus 3. On the right-hand side, the first thing I would do is distribute the 2 into the terms inside the parentheses. 2 times x minus 2 is what you'd get there. And then you'd have to add 3x and then add 5. Now on the right-hand side, I can combine some like terms. When I add 2x plus 3x, I get 5x on the right-hand side. When I combine -2 and +5, I get a +3 on the right-hand side. Now both sides are as simple as I can make them. Now the usual thing we do next is get rid of a variable term on one side so that all of our variable terms are on the other side. So we would, let's say I wanted to get rid of the 5x on the left-hand side. Then I'd subtract 5x from the left-hand side. If I subtract something from the left-hand side, I have to do that on the right-hand side as well. So I get 5x minus 5x plus 3 is equal to 5x minus 5x plus 3. And all of a sudden, the x's go away. And I just get this statement that says 3 is equal to 3. Now that statement, just as a note, is always true. 3 is always equal to 3. I'm just writing that down so that we can see it. That's not the solution here. If this is always true, and it's equivalent to this first equation, that means that this first equation is also always true, regardless of what you plug in for x. Let me state that again. This equation is always true. It's equivalent to the first equation. Therefore, the first equation is always true, regardless of what we plug in for x. And therefore, the solutions that we get here are all real numbers. So the solution is all real numbers. Every real number you plug in for the variable x will lead to a true statement. It won't always be 3 equals 3, but it will be some true statement. So all real numbers is the solution. And by the way, there is a shorthand way of writing all real numbers. If you go and to write all real numbers, if you write a capital R with like a double side on the left-hand side, that's the symbol for all real numbers. On Microsoft Word, it gives you this symbol here. But a lot of times when people write it shorthand, they'll just write 2 slashes on the left-hand side and then the R like that. So they won't double up the right-hand side real. But all real numbers is the solution. That's the point. And then the shorthand version, again, depending on how you type it, is one of those two. Let's look at the next equation. Now, we're not going to do as much with this next equation because I think people see what's going to happen. What is going to happen is, since both sides are as simplified as I can make them, I would get rid of the 2y on one side, and therefore I'd have to get rid of the 2y on the other side as well. And I would end up with an equation that says -8 is equal to 6. Now, in the real numbers, that is never true. Right? In the real number system. And just like this one, this first equation was always true, so anything worked. This one is never true, so nothing is going to work. There's going to be no way you can plug in a number for y into this first equation and get a true statement because it is equivalent to something that is never true. So that means there's no solution to this linear equation. And no solution also has a little interesting symbol. It looks like a 0 with a slash through it. It's called the empty set. And it's this symbol on Microsoft Word. So 0 with a slash through it. That means there's nothing that works. So if you do end up saying this symbol for all real numbers or this symbol, this is again the empty set for no solution. That's what it means. No solution, and this symbol, all real numbers, and this symbol. Now, these are the two unique cases with linear equations. With linear equations, if the variable drops out, then my equation is always going to be true or it's never going to be true. So I get all real numbers or no solution. Those are the unique cases. In all other cases, they're going to look like our previous examples where our variable stays in and we can simplify to get variable equal to a number, variable equal to a number as a solution. And that's what's going to happen most of the time. So these are actually the three options for solving a linear equation. You either get variable equal to a number, that happens most of the time, or you end up getting the variables dropping out and getting all real numbers or no solution. Like I said, most of the time in this class, when we solve a linear equation, we will get the single variable equal to a number answer. And that's what you get in these two equations. So why don't you try example 5, push pause on the video, and then try to do these on your own. In a couple of seconds, I will show you how these both are done. All right, here we have 5x is equal to 2 times the quantity x minus 1. I'll distribute that 2. That will give me 2x minus 2 on the right-hand side. Then I would try to get all of the variable terms with x on the left. That means I need to subtract 2x from the right-hand side. If I subtract 2x from the right-hand side, I need to subtract that 2x from the left-hand side as well. That maintains equivalency, and I'll get 3x is equal to negative 2. Dividing both sides by 3 gives me 3x over 3 is equal to negative 2 over 3. So x is equal to negative 2/3. Again, if it asks me to give a fraction answer, it's negative 2/3. If I have to round that to a couple of decimal places, that's approximately negative 0.66667. Or let's say we rounded it to 2 decimal places. That's negative 0.67. I'll leave the answer as x equals negative 2/3. By the way, you can go ahead and plug that in for those two values and see that you get the same answer as a check if you'd like. On this next equation, we get 7y minus 7 is equal to y plus 18. I would subtract y from both sides. That'll get rid of the y on the right-hand side. I will get 6y minus 7 is equal to 18. And when I add 7 to both sides, 6y minus 7 plus 7 is equal to 18 plus 7. Again, a lot of times if I'm on the board, that'll be underneath. That'll give me 6y is equal to 25. And then I'd have to divide 25 by 6. Now, again, 6y over 6 is equal to 25 over 6. Depending on how people want the answer to be written, they might ask for a decimal, which would be about 4.17. It's 4.16 repeating. Or they might ask for a mixed number, which would be 4 and 1/6. Or they might ask for just the improper fraction, which is 25 over 6. I think I'll leave it as the improper fraction in this case. Notice that it is perfectly fine to get these fractional answers, whether it was negative 2/3 in the last example or 25 over 6 in this example. That's a perfectly legitimate number to have. The last concept we're going to look at in this video is that sometimes equations might not look linear and in fact might not even be linear to begin with. But we can do some algebraic operations on both sides, maintain equivalency, and then turn them into linear equations. Now, one example of this is with rational equations. Rational equations are equations which have variables in the denominator. So if I have an x in the denominator of a fraction, maybe I can do some algebra to get that x into a place or turn that equation into something that looks like an equivalent one. So let's go ahead and do that. Here we have 3 divided by x plus 8 is equal to 2. I want to solve this equation. And it turns out there's a couple of different ways to solve this equation. I'll show you a couple of them. Now, there's actually probably lots of different options, but I'll just show you 2. So here's one option. Option 1 is to look at the denominators and look for a common denominator. And I'm going to multiply both sides by a common denominator to begin with. All right. Now, there's only one denominator here. So the common denominator just is looking at the denominators and saying, what can I multiply each by? The common denominator is x. So x is the denominator, and therefore I'm going to multiply both sides by x. I'm going to take 3 over x plus 8, and I'm going to multiply that entire side by x. And then I'm going to take x and multiply it by the other side, which is just 2. Now on the left-hand side, when I multiply that first term, I'll get 3x divided by x. Then I would get 8 times x. And then on the other side, I'd get 2 times x. Now here's the trick. X divided by x is just a 1. So those would cancel each other out, and I would end up with 3 plus 8x is equal to 2x. Now I would subtract 8x from both sides. I'm not going to show that step. We've done that a number of times. When I subtract 8x from both sides, subtracting 8x from the left would get rid of the 8x. Subtracting 8x on the right would give me a minus 6x. And then I would divide by a negative 6. Now 3 divided by a negative 6 would be equal to negative 6 over 6 times x. So just x. And then I can rewrite however I'd like. If I wanted to write my answer as a fraction, I'd probably reduce that to a negative 1/2. If I wanted to use a decimal, that would be the decimal point, negative 0.5. So multiplying both sides by a common denominator is always a trick that will work. That'll get rid of my denominators. And then I end up with an equation like this one, like 3 plus 8x equals 2x, that I can solve for x. By the way, we always want to check our answers here because sometimes we get answers that don't make sense. Like for instance, if I would have gotten x equals 0 and then tried to plug it in, I could not have divided by 0, and that would have been a problem. 0.5 or negative 0.5 is perfectly okay to plug in for x. And if you do plug that in for x in my original equation, you'll see that you get a true statement. But you do want to check answers here, especially on these where we have to multiply by variables. Now, as far as option 2 goes, option 1 was multiply both sides by common denominator. Option 2 is going to be rewrite until we get fraction equal to a fraction, and then we'll cross multiply. So we're going to rewrite and then cross multiply. So that's what I'm calling option 2. We have 3 over x plus 8 is equal to 2. So the first step that I'm going to do is I'm going to subtract 8 from both sides. Again, I'm not going to show that step. We just got 3x is equal to negative 6. Now, negative 6 on the right-hand side is the same thing as a negative 6 over a positive 1. And then what you could do is you could cross multiply. That is, I'd take 1 times 3. That will be the left-hand side of the equation. And x times negative 6 and make that the right-hand side of the equation. So basically, a lot of times you'll see people do this. Now, this technique only works when we have fraction equal to one fraction. So when I have one fraction equal to one fraction, I can do this technique. Otherwise, I won't be able to do that technique. So in this case, I would get 3 is equal to negative 6x, and then I divide by negative 6, just like we did before. We would get 3 divided by negative 6, which is negative 1/2, as the x. So again, cross multiplication only works when I have single fraction equals single fraction. And then I can cross multiply. By the way, the reason why cross multiplication works is because you're actually multiplying by a common denominator. If I multiplied by a common denominator, it'd be 1 times x. And so I can multiply x on the left and multiply x on the right. Let me write x and then multiply the right-hand side. Or multiply 1x, I guess. 1x on both sides. And notice that this x would cancel out with this x. I'd get 3 times 1, which is 3. This 1 would cancel out with this 1. I'd get negative 6 times x, which is negative 6. So cross multiplication works because it's multiplying by a common denominator in this thing. When I have fraction equals fraction, cross multiplication can work. And there's probably lots of other techniques that I could do that are maybe more complex. But here are 2 that work really nicely. Rewrite into fraction equal to a fraction and cross multiply, or multiply both sides by a common denominator. Let's do another example. Now, if you want to try this on your own, go ahead and push pause on this video and try this on your own. Otherwise, I'll show you how it's done in just a couple of seconds. For this example, doing the cross multiplication would be tough because I would have to add fractions And these fractions don't have common denominators, so adding fractions would be tough on the left-hand side. I have to do more work than I need. So what I'm going to do is I'm just going to multiply both sides by a common denominator. Now, the common denominator that I'm going to choose is going to be 12x, because 12x is divisible by 4x, it's divisible by 6, and it's divisible by itself. So if I multiply everything by a 12x on the left and right, I will get rid of my fractions. By the way, when in doubt, you can always do this by hand. Just ask yourself, what do I need to multiply to get rid of 12x, 6, and 4x? It has to be divisible by 4, divisible by 6, and divisible by 12, and obviously have an x in it. So that's what I'm going to do. I'm going to take 12x and multiply the left-hand side of that equation by it. And I'll take 12x and multiply the right-hand side of the equation by it. Now, what's going to happen is 12x times -1 is going to give me a negative 12x over 4x. 12x times 5 over 6. Well, 12 times 5 is 60. So I'm going to get a 60 over 6 as my second term. And then when I take 12x times 17, I'm going to get 204x divided by 12x on the right-hand side. All of those things can simplify very nicely. 12 divided by 4 is 3. X over x is 1. 3 times 1 is 3. So I end up with a negative 3. Oh, I'm sorry, I missed the x there. Should be 60x. I apologize. 12x times 5 is 60x. Forgot to write that down. So I get negative 3 as the first term, and then 10x as the second term. When I take 204 divided by 12, I get a 17. X over x is 1. So this is what I get. Negative 3 plus 10x is equal to 17. And this equation is straightforward to solve. You can solve just like any other linear equation in one variable. I would add 3 to both sides. I'm not writing that step. I'm just gonna, when I add 3 to both sides, I get 10x equals 20. And then I divide both sides by 10. Dividing both sides by 10 gives me x equals 2. So that's my final answer, is that x is equal to 2. And as always, if I want to check that, I can plug it in to this very first equation. I can check that by taking negative 1 times, or excuse me, divided by 4 times 2, plus 5 over 6 is equal to 17 divided by 12 times 2. This would be negative 1 over 8 plus 5 over 6 is equal to 17 over 24. And on your calculator, if you take negative 1/8 and then add 5 over 6, you do indeed get 17 over 24. So this is a true statement. And so that confirms that x equals 2 is the solution. So there you go. Multiplying both sides by a common denominator will get you an equation that has no denominators in it. That'll lead to a solution, hopefully. And then you plug that in to check, make sure you actually get or got the correct solution. Here's another example with a rational equation where we have x's in the denominator. But in this case, we have an x plus 2 in the denominator. That's different than 2 times x. When I have an x plus 2 in the denominator, I have to treat that x plus 2 as a single unit or a single numerical value. So let's go ahead and solve this equation. If you want to try this on your own, push pause on the video. In a couple of seconds, I will show you how it's done. Once again, there are multiple ways of solving this, but I'm going to solve this by multiplying by a common denominator. Now, to get the common denominator, what I would do is I would say that since we have an x plus 2, I need an x plus 2 as a single unit. Now, I'm also going to need a 2. That's different than the plus 2 that's inside here. So I'm going to need a factor of 2, and I'm going to need a factor of 4 for this number. Now, if I have a factor of 4, I also have a factor of 2. So technically, I can write just a 4, and that'll also include my factor of 2. So the common denominator that I'm going to use is 4 times the quantity x plus 2. And I am not going to multiply that out, not at this stage anyways. So now what I do is I take my equation and both on the right and the left-hand side, I multiply by that common denominator of 4 times x plus 2. So I write 4 times the quantity x plus 2, 4 times the quantity x plus 2. Now we have to be very careful when we do this multiplication because we're multiplying these two numbers times this fraction and these two numbers times this fraction. So we take 4 times 5, that would give me a 20. But then I'd also have to multiply by the x plus 2. I'll leave that in parentheses. In the denominator, I have an x plus 2 on that first term. Then I'd take 4 times x plus 2, and I'd multiply by 3 over 2. 4 times 3 is 12. So what that would give me is 12 times the quantity x plus 2 divided by 2. And then lastly, on the right-hand side, 4 times x plus 2 times 35. 4 times 35 would be 140. So I'd get 140 times the quantity x plus 2 on the top, and then divided by 4 times the quantity x plus 2 on bottom. Once I do that, then where I have an x plus 2 in the numerator and denominator, those will cancel. So this x plus 2 will cancel with this and just give me a 1. This x plus 2 will cancel with this one and give me a 1. And I'll just have this x plus 2 left. So I'll have 20 plus 12 over 2 is 6. So I'd get 6 times x plus 2 equals 140 divided by 4, which is 35. By the way, you could have, if you wanted to, in this case, you could have canceled the 4 and canceled the x plus 2 and just been left with 35 there on the right. So this is the equation that I get, and that is a fairly straightforward equation to solve. 20 plus 6x plus 12 is equal to 35. 20 plus 12 is 32, so I get 6x plus 32 is equal to 35. Subtracting 32 from both sides gives me 6x is equal to 3. And then dividing both sides by 6 gives me x is equal to 0.5 as a decimal, or 1/2 as a fraction. So that canceling out of the x plus 2's really does the job. I'll erase that. If you want to, you can test out your answer by plugging it in. 5 divided by, this is going to be 2.5. So 5 divided by 2.5 plus 3/2. That'll give me 3.5 on the left. And then 4 times, this will be 2.5. 4 times 2.5 is 10. So that's 35 divided by 10, which is also 3.5 on the right. So checking my answer confirms that I do get x equals 1/2 as the final answer to this linear equation. I should say this is the linear equation. Technically, we started with a rational equation. If you're having a hard time finding common denominators, then you can always just take whatever terms I see and multiply them together. I see the term x plus 2, I see a 4, I see a 2. I already have a copy of x plus 2, so I don't need that again. So I could always have taken 4 times 2 times x plus 2, that's 8 times x plus 2, and use that as well. So there's lots of different options for common denominators, but they all have to be divisible by 4, divisible by x plus 2, divisible by 2. Obviously, you can do more examples if you'd like, but the main thing is always simplify both sides of the equation. Sometimes, like in the cases when we were dealing with fractions, simplification meant multiplying both sides by a common denominator and then simplifying. So simplify both sides of the equation as much as possible. Force variable terms on one side of the equation, force constant terms on the other side, and divide by the coefficient of the variable. This is the way to solve linear equations in one variable. Again, simplification can mean multiply by common denominator and also just combining like terms, using the distributive property, those types of things. So that's it for this video on solving linear equations in one variable.